to hey, Coffee Compiler Club. We're here to talk about, I don't know, giant houses and where people live and buying land and maybe compilers and language runtimes and typing systems and register allocation and stuff like that too. You're gonna record live, be on YouTube within a couple hours. No set agenda. Someone wanted to start. Let's see.
I think from the last time, Darrick has an interesting follow-up on the sea of nodes.
Yeah, I've got some stuff. Well,
Yeah,
so I was working all week on Sea of Nodes, my Sea of Nodes implementation, and I actually got one version working to a certain extent, and then I decided, oh, now with that experience, I know how to do it better. So I started redoing a big chunk of it, and I almost got it done before today, but not quite.
excellent.
So, but yeah, so I'm kind of aided and hindered by this, by the fact that I also wrote a graph database library about a year ago. And so I'm using that, but I'm also finding all sorts of ways of improving that. So a couple of the days this week was just working on the graph library itself.
Gotcha.
But it's all for the best.
Yep. Yeah, I get that.
So yeah, unfortunately I can't show much today, although I have some like drawings I was making while I was working through it. And then one of the things that came up a while ago that I kind of want to show off and see what you guys think a little bit is the sort of, well, I mentioned a while ago that I was compiling from Python. And so I changed, I mean, it's still compiling from Python, but I've changed it so I actually compile to Clojure, then I do macro expansion, and then I continue on the compilation. So that lets me do a lot of my more basic language features as macros, and I don't have to put them in the compiler. That's actually worked out pretty well. So I thought it might be interesting to show that.
So you're
that
saying
actually does work.
So you're saying you re-implemented with pre-compiler?
Yeah.
I guess so. Like I use the Python AST library. I kind of talked about that to like deal with the mess that is Python syntax, and then I go straight into Clojure, which is a fairly direct conversion actually. And then,
I mean, I think Lisp's S expressions were originally invented to be an intermediate representation, right?
Yeah,
They definitely were part of that. Yeah. Yeah.
It certainly works pretty well. And so I do that up and for a few passes, and then I have a bunch of passes that take it all the way to bytecode, and I can run code based on that. But I've sort of I'm in the process of replacing most of those passes with Sea of Nodes. So it's actually funny how many passes get replaced, but
yeah,
and how much nicer it's turning out. So
that's why it's there. So the hotspot compiler has a toolbox piece that will let me stitch together pieces of Sea of Nodes to do what you're doing for your macros pass. Because I get bytecodes that have funny expansion patterns, or I wanted to take the math.min and math.max and not inline them, but essentially macro expand them, and then that's just done with. I won't say it's a macro, but I start with a pattern match of the funny intrinsic I'm going to inline, and I have a toolbox that just makes symbols parts. It gets a very similar effect.
Yeah. Oh, and so the way that I do all of my pass definitions is I have this library I created called Pattern. It's on GitHub, but it basically does pattern matching and rule expression. It's pretty flexible. And one of the things I can do with it is add like pattern matchers. So I added some graph pattern matchers, and then ended up doing all of my I can show a couple of the transformations. Like I do the Sea of Nodes transformations through these like tight little patterns.
Yeah, fine. I can show you what the code that I write looks like, and I'm just kind of curious to see compare, because I haven't
Sure.
long thought about and toyed with in my head having a little more official pattern matchy, and then many
Yeah.
patterns are simple and straightforward, but there's a fair number that are out of the box. I mean, they're not so easy.
Yeah. Yes.
Yeah, I'd
So-
love to hear one thing that you thought was obvious to do as one of those little peepholes, and one thing that you thought was non-obvious as to how you would do it as one of those peepholes.
Oh,
Yeah, I think I'm probably only doing the obvious ones now. Why don't I show? I'll share
Yeah.
my screen. I'll start with that. And
oh, share
I
screen.
need to-
You're talking to me. Hang on. Okay, try now.
All right. Okay, sorry for the dark background.
Doomed.
Okay, so this is the pattern matching on Sea of Nodes right now. So basically, the way that what I decided to do is I have this little vertices come in, and so it's matching against vertices. But I have this little question expand matcher, and it basically, if it receives a vertex, it expands it into something that looks like an expression where each of the items in the expression are other vertices. So that I can kind of recursively.
So in the Sea of Nodes, there's nodes and edges. You're following the edges to get more nodes. Is that
Exactly. So, but this double knot one is a obvious simple one.
Yeah.
But a vertex comes in, it's not. It'll match if the operator is the symbol not. It just puts it into this position, and then there'll be an expression vertex here, and it has to follow the edge to get to that. And then it then expands that vertex, and if that's also got not as the operator, then it just matches E, and I just want to return E. So then the result is that the vertex that was the overarching one is replaced by E. And so basically there's a runner that's going through the work list, gets each vertex in turn, throws it through the pattern matcher, and either if the vertex itself comes back, as in it wasn't changed, then it moves on. If a different vertex comes back, then it says that must be the replacement of this vertex. And then because it's a bit of a pain in the butt to create vertices, what I'll do is I'll return what this sub does here. If we look at this expression here, this creates an expression where it's basically an S expression if and this, it's like a combination of vertices and expressions, and it just parses through it, pulls the vertexes out, and creates vertexes wherever there's an S expression. So it kind of reparses this, and that's kind of that lets me keep the rules very tight and small.
It's like taking the wrinkles out on an ironing board.
Well, I'm trying to sort out how that worked yet.
Because he returned
Yes.
an S expression, right? And then he has to iron it out into a vertex, right? Did I follow?
Exactly. Yeah. So there's one place that it's parsing kind of, it's like a pass that it does over the result of this rule expression. So if it is a vertex, then fine, you just use that. If it's an expression, then I'm going to parse it through and
it's a
create
deferred
vertices
vertex.
where there's an S expression, and anywhere where there's a vertex sitting in the S expression, that is going to be attached into that place in the wrapping vertex. So that seemed to be quite nice. It lets
That's
me
cute.
restructure things pretty efficiently. And so I ended up, I have a bunch of things that, here's rules for combining constants. So Yeah, I can. So this one is just a binary operation with 2 integers. And so this basically says if I get a vertex, I expand it into the actual integer value that the vertex represents. So it'd have to be a constant vertex, and it pulls out the int, and it sticks the int into A here and into B there. And then this is saying I'm going to grab the actual operator, which is the in the overarching node, and I'm going to only match it if there's a mapping from operator to function. And then in the body, I grab that function, I call it, and now I've got a new constant. And then so that comes back to the rule runner as a constant, and it's going to get folded into a constant node and replace the old expression.
So I break out constant folding from graph reduction because constant folding admits to a optimistic and a pessimistic version, and the graph reduction can only do the pessimistic version. So there's an opportunity to replace the constant math with a stronger algorithm and also have it work exactly as you're doing it here. So I break it out as a separate thing. And for me, I make a virtual call against a Java object that's the underlying node and say, compute your new value.
Yeah.
We'll look at his inputs and produce a new value. If the value he produces is a constant, I'll do a replace call that says swap you out with a constant.
Yeah.
So it's very similar, except that it's not limited to things that have what I define as constants. Pretty much everybody can do it. So if nodes and call instructions and your basic primitives, obviously, but everybody can turn into a constant at some point. So it covers more ground than you had to be a primitive int, because I can get constants out of loads off of structs with constant fields and things like that.
Yeah. Actually, I was thinking about the fact that some of my global variables are constant, or they may be constant. Like, yeah, some of them are going to be constant. They're defined and then never really changed. So I might as well treat them as a constant. I'm not quite sure how to match that yet. I guess that's is that because that's an optimistic?
No, the optimistic is a change in algorithm, but not change in the match or the computation. The computation is for a given node of any kind, including control or data computations like an add of any kind, you produce a value for it. Every node has a value. So an if instruction takes in a predicate, and it takes in a control, and it produces 2 controls out on the true, one on the true, one on the false side. That's part of the sea of nodes from the presentation I did a couple weeks ago.
Yeah.
And those edges flow into regions or whatever emerge for those control, who then ask that question again. And at any point you can say, I have a value here, which is control or unreachable. What you're calling reachable and unreachable.
Yeah.
I use X control and control, but unreachable is great.
Yeah.
So the output of an if is actually is a tuple of reachable, one for the true, one for the false. So it produces a tuple value directly. And that's its value. So when I say, Mr. If node, compute your value, I get a tuple back. If that tuple happens to be both X controls, that if node can't be reached. And maybe that turns into some control flow collapsing. Now, usually control flow collapse happens out of region. So if one of those outputs goes into a region and I come up to a region, now I'll do I can do the value call, the region's reachable if any of its inputs are reachable. But also the region can do the collapse that says, I have an unreachable input because I'm running the pessimistic version here that's guaranteed unreachable. I can just delete it. And all the fees that are tied next to it, they all delete the corresponding value that gets merged in. And then you get dead in the sea of nodes and rolls up. But that's all done on the value computation to get the reachable or unreachable point. In addition to values being used for integer math and float math and all that kind of shit, it works on control flow just fine.
Yeah. One thing I think I've done wrong, which I haven't dealt with yet, is I've I just threw all my nodes into a giant set and treated the set as my work list.
Yeah, that's
But
what I do. I have a work list, so it's actually a work list. So the set of them shrink to start with. Throw all on the work list. Yeah.
But then isn't there a like I should really be pulling only, I should start from like the return values and just walk backwards.
So you actually walk forwards for constant propagation. You only walk backwards if you're doing liveness, which I'm also doing, but that's another story. I have a different one. So
Well, so if I change any node, then I put all of its users back on the work list.
no, you're close. Yes, you put all of its neighbors on the work list,
All of its
unless you
neighbors.
only have matching rules that go one way. I routinely have matching rules that go both ways. So
Yeah, so I thought about, I actually think I created a matcher to say like, give me the users,
right.
but I haven't used it.
Right. Okay. So I thought long and hard about a matcher that said, give me my inputs at one step removed and my outputs, do a pattern match. And then if something changes, all my outputs go on the work list because the patterns are so simple. And the usual story is just what you did. You return a replacement node. You have an add of 0, you replace it with the thing you just added.
Yeah.
So it's a replace game. As soon as your rules get more complicated, that doesn't work. And I certainly have rules where that happens. So like a region which has several inputs, some go dead, I return a copy of itself with the missing guys removed, but I have to have all his fees remove the identical edge at the same time, because otherwise they don't know which edge got nuked. Right? They had a 3-input merge or a 4-input, a 3-input merge. I'm moving the middle one. I have a bunch of fees. They all have 3 inputs plus 1 pointing to the region, so they know where their region parent is. If I nuke the middle one and I don't nuke the middle of these 3 on the fees, later in life, when I come around to the fee, I don't know which one of the 3 I should have nuked to align with the region.
So I actually went with your older compose select structure. So I think I'm okay because the select point to where they go.
Okay, that does not compute, because
okay, let me show different thing here.
Yeah, so regions and fees is one example, but let's just go with that for a minute, where you want to do multiple updates in one shot. Having decided you've pattern matched, you're updating multiple nodes. And that was what I was trying to get at. And then as soon as I do that, I start getting to, places where I go multiple directions. Yeah. So that's an if projection, if yes. And on that's the one where you've split. Now go to the reverse side where you've got a region merging, and you've called it tail, which is only true if you have sort of simply nested control flow. And then what you're saying is select. Yeah, so select is missing some edges here because you're going to select, or you have 2 selects. Okay, a fee would have one. A fee would say I have a control to
this is the control.
Yeah, I would have a control point to the tail, and then I would point to the classic SSA fee node has a control point to the tail and data inputs pointing to each of the things to merge.
Yeah, that's these.
And instead you have different 2 nodes for your select for region for fees.
It's kind of part of fee. They're like, so select is saying that this fee has 2 things.
Oh, I see what you're doing.
It basically has Z and
I don't have selects at all. They're not necessary to have the select at all.
Yeah, what's the function of these selects?
Well, do you want me to pull up Cliff's paper?
Yeah, I don't believe I've used select in a paper either. That's not a thing that I've done.
Really?
Yeah. So there's a misunderstanding. I was going to whip out my easy SSA presentation, but you probably want the paper instead.
Okay, hold on. I got the paper right here.
Okay, yeah, slap it up.
This is from quads to graphs.
Yeah.
So here
Select
you've got
fees.
compose select. Sorry
Oh,
for
this is
the,
like the really old one. Oh my God.
yeah.
Okay, maybe you're right. No, no, I ditched that
Well,
one.
this is from the
Wasn't
early
ago.
90s. So if you know,
Yeah.
it's not surprising if, but anyhow, it seems like it, to me,
Wow.
it seemed like it made sense.
Y-
And I like the
yeah.
fact that the fee loses the positionality
Yeah.
because
You have
you,
extra nodes in the graph and the fee loses position. I see what you did.
yeah.
No, wait. Why, if you nuke a control edge, you still have to match the nuking compose edge.
Well, if
Suppose the back edge of the
the
loop.
select goes dead, I can just pattern match against that and then kill that and then pattern match against a compose that's no longer required.
So the back edge of the loop dies, for instance.
Yeah, let me go back to the
Oh,
other.
then it does feed into select. Yeah, you're right. Okay, that'll work. Fine. That works.
Yeah, so basically what I can do is say I kill this guy.
No,
Now
back
this-
edge control.
Now this
back
guy's
edge.
dead. Now this guy's dead, and this needs to get repointed to there.
And then the select goes dead.
Yeah, and then this goes dead, that goes dead, this goes dead.
You've done a weird thing to yourself because you've made a infinite self cycle.
Yeah.
You have straightforward control flow. Where's your loop? You don't have a loop here.
This one doesn't have a loop.
Yeah,
This,
well, right.
I've
so
got
you-
one with a
you
loop here.
can't- We stitched something together incorrectly with that dude.
Oh yeah, maybe I did. Oops.
Fine, you did live demo, so you know.
Yeah, it's probably,
So you're saying the negate, suppose the negate becomes a known constant, or the equals 0 becomes a known constant value. The if is going to collapse to just the true side, or just the
yeah, okay. So if that happens, then
that becomes a constant.
so that's 0.
Yeah, right.
So then this goes away. So then basically,
Keep nuking and do your undo function. Nuke the proj else just claims, or
right?
actually
So,
it's proj. Right, fine. Okay. And
yeah,
then the else goes
this
dead.
goes,
Yep,
this goes.
because it's missing an
Okay,
input.
that must go. This,
Should
now-
go and just become replaced with the select. So get rid of the result thing.
that would,
This your
That-
function return result is
yeah,
yeah, and then that's going to roll up to the RZ. Okay, your function is going to return Z because that's what happens if it's false.
yeah, exactly. So basically it comes here, this
So
all
those all die.
goes,
That all dies.
that
all
goes,
dies.
this.
Yeah, that all dies. So that's the loop I was thinking you had, but you don't. You're just returning Z. Your
Yeah,
function returns.
So basically it goes to this.
Yeah, exactly. Yeah, which is fine.
Yeah. so-
Your layout was a little odd for me. I have a return node, not a pointer to the
Oh yeah.
function header for the return and things like that. A little different layouts, fine.
Oh yeah. Yeah. Um,
Yeah,
Clarify,
fine.
just to clarify on select. So is it the way to associate control with specific fee value?
Exactly.
Yeah,
Okay.
Yeah.
I-
So it's
I-
just control and value.
I used the classic fee instead, although in that very early paper, fees were not like widely known, and so there was the select there.
Yeah. Yeah. You talked about that a while ago.
Forgotten that that's very old.
Yeah. But I thought it was good. And, you know,
Okay. Like I said, I use fees because everyone gets fees, and then you do a multi update, and then the multi update like that. So I can produce a different multi. I guess my original point was pattern matchers that only return a singleton node are really cool looking and have serious limits.
yeah.
One of them is they can only update one node. One of the limits is they can't look too far afield to do their pattern match. Or when I look at my patterns, I routinely have patterns that look more than one node afield.
Yeah.
And
So
the debate is how finely do I slice nodes such that I only need to look ever one node afield and I can
Yeah.
fold it up. It becomes
Yeah.
a little conceptually simpler in a lot of places for me to say, no, I'm going to look multi-nodes afield. And then my neighbor list changes more aggressively because I depend on somebody who's further afield. So he counts as
Yeah.
a neighbor.
So my first iteration of this was the same pattern matching, but actually doing the graph manipulations in the matcher. So it's something I can do. So I think what I would probably do is split those into separate passes or rule
Okay, I
types.
don't do them in separate passes, but having I do a pattern match that return. I have a bunch of them. I have a pattern match which returns a node, which is your replacement.
Yeah.
And he stitches on the spot. And I have a pattern match that it's the same match. If he returns the self node, he doesn't do any updates, and the pattern matcher himself, does updates as he goes.
Yeah.
So if a
Yeah.
region decides to drop a control input, he'll return the same region because that region still exists to merge the remaining inputs, and he'll delete the input on the region and the matching input on all the fees.
Yeah.
Then he'll put the neighbors of the fees as well as the neighbor of the regions on the list. And the main pattern match rule invoker, seeing that you came back with a self node, knows he's not doing anything about it. He doesn't do any graph updates or any neighbor updates.
Yeah. 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 So I think this one, it's a bit more complex because I originally had this whole environment that was flowing through in addition to the nodes. And so I was like, I didn't have everything in the graph, and that was a disaster. And so complexity went crazy. And so that's why I was doing the rewrite. And plus I came up with well, why don't I just do parse out my results and, the thing I was showing before. So
I'm looking at your identities as well. So I also run an identity call that just says you're a simple replacement of exactly some other node without any further magic.
Yeah.
So it's a replacement with an old node as opposed to replacement with a new node. And the reason for that one is, again, there's an opportunity for an algorithm that runs that gives a sharper answer. In particular, fee nodes fall prey to that a lot. You get extra fees, and if you can say this fee only merges one input, there's an identity on the one input, there's an algorithm.
Oh yeah, yeah, and I actually have that one. It's remove trivial fee, and so I basically say compose, and I say, okay, I capture the input node as this, and then also expand it, and I say, okay, it's right now it's always coming in as the second node. So I'm basically saying if there's a value in the first node and this and the second one, then I remove it and I basically delete.
Here, I'm going to yank, share, and show the equivalent code. See here, how badly. Oh, and Matt wants in. I don't know how to get Matt in from here. Matt, yes, admit Matt. Okay, fine.
Blinding white screen.
Yes, isn't that amazing? All right. People want me to raise my font size.
Yeah.
But let's try, something like this. So here is this code. So if I get called nested in mid construction, there's a cutout. If I know that I am dead, somebody else is going to cut me out. So if my value is 0, let's say it's my input edge 0, points to a node, points to a type thing, which is type unreachable, X control. Don't do anything now because the dead code eliminator is going to wipe me out. Otherwise, it has to be a region node. That's a control flow merge. There's an assert. This is identical to the prior guy. I probably shouldn't have that test. It's just if the input is already dead, I'm dead. There's a test because regions double for heads of functions. And I have a debugging hack that says, don't inline this function, and then ignoring that one. So get down to the body of the code, walk my inputs on that feed. If the input is dead, so the matching regions value as a value like an int or a float is unreachable, ignore it. So that's the continue. Get the thing that I would be merging, see if I've got it or it's live. So I can ignore myself or duplicates. If I'm merging the same thing multiple times, just keep ignoring. Otherwise, I have something I haven't seen before. If I haven't seen anything, I just record it under this live variable, it's just a local variable. Else I found 2 or more unrelated inputs and I give it up. When I come out the bottom here and I say, if I have a single guy and it's not me, it's the unique input and I return it. And then the ideal reduce is called by a guy who says, you're replacing one with another, just swap them out and do all the graph rewrite edges. So no rewrite edges, it's just an inspection. So it's what you just showed with a little more, you know, I got a little less clean, a little more detail and some debugging hacks. And I support
and so can do you think the like the X control stuff or the unreachable stuff can be split into a separate pattern, or like I'm just wondering if I can keep these things separate.
I found it very convenient to not keep them separate because the collapsing of control flow feeds the collapsing of data flow, feeds the collapsing of control flow back and forth and back and forth. So if you forcibly separate yourself, you'll just end up calling them back to back to back anyhow.
Right.
So I throw them on the same work list and let them go to town. Now, you might have a different case. I'm doing random junk Java code. I have a million bonus checks, safety checks, of which 90% are dead, right, or redundant. There's a huge count of them that are dead or redundant.
Yeah.
And so this kind of collapse happens to me all the time. And
yeah,
you might be in a different zone where you don't care.
Yeah. Well, I mean, I was looking at, I actually think that a lot of this collapse will happen, especially with function inlining.
And then if you saw my little comment here about fee nodes, so for me, region nodes, function headers inherit from region nodes. They're just
I did the same.
point.
Yeah, that was something that was actually a bit unclear because all the papers and everything, it's always presenting from the perspective of a function. And it's a bit hard to figure out. I had to kind of think about how it actually integrates into the whole program.
So here is, fun node extends region node. So function header is just a region header plus some extra functionality bits.
Yeah.
And a parameter node extends
and how
a
do
fee
you deal
node.
with arguments? Because that was another thing that's not, I ended up making little arg nodes, you saw.
Yeah, I have parm nodes for your arguments. They're numbered going across.
Yeah, okay.
So I have some convenient way to go look at them. They extend the fee node. So if you have unused arguments, I'll collapse them away and shit like that happens.
Oh, well, so unused arguments, like they're not used in the program body.
Once I'm done building, so I'm a little different scenario than you are here. So once I'm done building the graph, I have included all possible inputs to all possible functions. I build a conservative control flow call graph. During the following phases, and during the conservative call graph construction, I'll discover I have made a call that can't ever happen, and I'll nuke that call edge into that function header. I'll nuke the call graph edge. That in turn nukes one of your paths into your parm nodes parameters. Also, if I discover that a argument is dead, then I'll nuke its use from all call sites.
Oh, okay, so let me understand this. You're treating the parameters as basically like phis, and every caller is a select or like an input into that phi.
Yeah.
And then if everybody agrees not to or if every path doesn't use an argument, then that whole thing gets killed in every user.
Well, the use goes away from every call site. A call might call multiple different unrelated functions. So the actual argument construction may still be alive for other call sites it's calling, but it won't be necessary to pass it on this path.
Oh yeah.
And when doing like separate compilation games and shit like that, you always end up with a unknown caller who calls with every possible worst case argument that forces certain things to happen to the parameter counts. You can't get rid of them. You have to have a hole in the parameter count for somebody who's going to call you with an argument that you don't care for. So there is a thing that happens there, but from the, the typing analysis point of view, argument's dead. I don't care what you pass me.
Right. Right. Yeah.
And
And then
in
I
fact,
guess you're always just
no,
keeping
it's
track
dead.
of any IO or state change stuff that might happen, and even in code that's otherwise sort of
So
the results are unused, and you just sort of do that.
parameter nodes come from fee nodes. Fee nodes understand the state of memory. There's just a normal fee node. He's typed for a memory type. Let's go look at fee node here. There's a type T that just tells me the type of the thing I know. Just a flag to signify scalar versus memory versus objects versus IO. Any of those. Fee node to merge IO too.
Yeah, actually, can I go back to the graph thing I was showing for a second?
Yeah. Should be good to go.
Yeah. Just had to find it. So there are a couple of things. So this one's a bit of a complicated picture.
This is why I quit doing graphs for
Yeah,
everyday debugging.
it's really good to
presentation. But
yeah, it was really good to understand it. But so here I've got somewhere compose.
so you're missing an argument for memory. You have two memory edges flowing into your function header. Change the function header to only take control from all the call sites that call it, including the unknown caller. If you're not yet, you're doing separate linking, there's an unknown caller. Add in.
Sorry, I didn't quite understand. So change. So this is a bit wrong. What should
I would change yourself to have an argument for memory. I called it a parm node. You have an argz there. Add an argument for memory.
Right. So this is just an arg as well.
Yes. It's a standard arc carrying a data. It happens to be a state of memory. You can make multiple memory edges if you're doing alias precision at function headers of various kinds.
Yeah, so I was thinking that because I have fairly simplified memory model, I would basically make every constant, every object that I create a separate memory object that I
splitting your memory state.
Yeah.
Still make them an argument, one for each of your memory, your X and your A, make them a separate argument, because what it tells you is this function can have the memory states from these different things coming in. And just be clear, these are variant objects. If are they variant, or are they truly constant? State of memory is constant.
These are memory, they could change. Somebody could set them.
But there's the pointer to them is constant. It's a global constant.
Location is constant, yes.
Yeah,
yes.
global pointer constant to a collection of memory that gets updated. So make an argument out of it. You're passing in the state of the memory, not the pointer. The pointer is truly a constant. You would treat the pointer like you would treat the number 5. It's just a constant.
Yeah, that's kind of what I was thinking of this as. So then, but yeah, okay. So basically there's the
you need the
memory, and then there's the actual memory constant.
Yeah. There's a memory address pointer, which is constant. Yeah. And then the state of memory is not related to the pointer to it at all.
Oh, really?
Yeah. Yeah. There's no, you can have a pointer or not, and you can update the memory without the pointer, or somebody else can update the memory without you seeing it, especially if you have an aliasing situation. You have memory updates that you don't have the same pointer to. You can pass the pointer along and never look at the memory, right? You can call another function who updates the memory, and then you come back and you pull out the change state of memory. But the two are not related sort of in any way. Stores and loads will relate them. A store node will take a memory state and a pointer, or a load take a memory state and a pointer and produce the value he loads.
So that's what this is here. So I'm storing 1.
Okay, yeah, you're upside down in your graph here. I would put the 1 above the store.
Yeah,
it's a constant, so you're sharing. Yeah, right. And now the store needs the address, which is a memory constant. That's your mem adder in gray. And it needs a state of memory. And that state of memory, I claim, should come in as an argument, because it will vary according to the call site where the function happens. So I would put that state of memory as parallel to argument Z. It's just another argument like Z is.
Yeah, yeah, okay. That makes sense, because I was kind of thinking that I was going to have to, that's why I had those edges in there, that I was going to have to deal with those memory states when I call the function.
And just like argz has a pointer to your function header, for me, it's a region, and the argz is a feed.
These
farm.
are regions as well.
Yeah, it same. So I put all my arguments on parallel with the function header, like move the function header above everybody. This is me doing graph layout games. And put the state of memories alongside the function, so I see the function header and his arguments all in a row, just like a make a function call would look like. And I don't know. That's how I conceptualize that piece.
Yeah,
but that's go do graph layout games.
Yeah. Oh, right. Yeah. So right. I mean, I was just trying to keep things from being crossed over as much as possible, even if they weren't necessarily.
Well, okay. So I tried this game 20 years ago, and several other people did too. It helps you to lay a graph out so it kind of sort of looks like your code would get laid out. You map your pieces, parts, and then you get weird crossing rules, and you want to vertically stretch to help cover the weird crossing games. But you want packages for your loops to, do what you have for your loop there, where your loop head flows down to an if, down to a projection, and a loop body, and back around as your red loop there. That one's kind of in control flow order. Yeah. But the arguments want to be on parallel or below the function header, because that's how I think about making a function call. And I'm in cast in a function. I got argument 1, 2, 3. State of memory is an argument. Right. So you kind of move this down here, and you've got these things sitting. Yeah, push that blue function header up like that. Yeah. Right. And then you have like that stores out of line somewhere. Yeah. And then stretch yourself vertically, and suddenly you have a function that's got all the parts laid out in function order. That's that makes sense. Look at it that way and see if you like how it looks. Yeah, that makes sense. So, and then the other thing I did here was simply you messed with these things for hours. You got a nice looking one. It looks really pretty. You have a good understanding, and then you change some little thing. You need a whole new graph. The layout has to be manually done again. It's too much work. I've actually got an awesome graph layout engine. Okay. That I just haven't tied into this thing yet. Yeah. So. Yeah, back in the day, it was like, I want to say VCG or something. There was some graph layouters, and nothing super awesome back then. So you didn't get so much help with doing automated layout. Yeah. So, because I've been doing a lot of graph stuff, like for other problems. And so there's this layout algo called Force Atlas that it can deal with 10,000 nodes and lay them out really nicely. And so I implemented that for my graph engine, and I have a visualizer for it and all this stuff. I haven't actually built a proper graph, so I can't do that. But eventually it'll probably be disgusting looking, but that was my experience. The other thing is, of course, is that you get, I got no graphs with like 100,000 nodes, and no graph layout was going to make something sensible out of that. You had to slice the graph. Yeah. Define slice regions. And so I just got in the habit of fancy pretty printers where I would do manual hand slicing by say, start from here and count 10, 20 nodes in, doing control graph only, and pretty print them as an ASCII text. And that worked out fine. Yeah. I have a little thing that I've been using to turn the nodes into S expressions. And then if it turns into a loop, it just prints the node ID. Yeah. So that actually I put node IDs in all these things when I pretty print them, and that just is part of the pretty printer puts the node ID up front, so I can do the, and then it prints them in order as a topological sort, except it loops where it's cleverly, aligning you, and you can see where the loop header starts and shit like that.
And you want to use a lexicographic trick on the IDs so that it doesn't collide with anything else in the graph. So you can highlight the ID and search the ASCII output for it.
The IDs are all unique. They're all small, dense integers that are unique.
Right. Yeah. But you may be printing out other integers inside that same output.
It's true. So I actually spent some time thinking about this, and So what I have is for my nodes, their ID is actually a little object that says node and the ID.
Oh, I
And
see.
then I have a hash object. I have a hash node, which just the node ID is the hash code. So then I can look up the hash node and follow one edge into my node.
I just, I got,
and then
but
I have these, what I call hash object, which is the object that I use to create the hash code. And I also store that as a node. So I can, and that's more for my own debugging. So I can say, and so at first I just went straight to hash codes. And then I was like, you know what, I got to create these hash objects because I'm getting confused. And then I had so many wrong hashes.
yeah,
And
you get a bad hash function. That's great.
I mean, the hash function was okay, but I was using wrong data to generate the hashes. And
Oh,
so
really? Oh, okay.
right. So like, you know, it's like, oh, this one, I forgot to put in one of the arguments. This one, I'm doing, why am I having all of my, you know, regions collide? It's because I forgot to include the node region name in the hash function. So the hash is just on the symbol region. Stuff
So,
like that.
so like I have a node number right in my Java object as a small integer.
Yeah.
And my hash function covers the 99% case and says your function as a part of your opcode as a small number plus the node numbers for your inputs are all hashed together.
Yeah.
That, like I said, it covers 99%. Constants have to have for their constant value.
Have you ever had to deal with hash collisions?
Yeah.
Yeah.
So stupid pet trick number 2 here. Pay some time to get a good hash function. So when I run these, you know, do big piles of both in C2 and hotspot, and when I do self-testing now in AA, and I use these hashes a lot. The original hash functions I started out with would have a high collision count where I would get thousands of nodes on the same hash chain. It was ugly. It was brutal. And switching, you know, paying a little bit of money, you know, time for a hash spreader got me such a better hash function. So these days, typically I have a, you know, 1.2 probe rate. You know, like 20% of the time I hit somebody and then I probe again and I go. So to ask your question, maybe I heard a different thing. I'm going to have a good hash function. I have an equality check. You can't just assume it's unique on a hash.
Right. Yeah. That's what I'm not doing right now. I think I need to. I'll have to do that.
The Bertle B hash function. I go pull that up again, throw it in the document here. Or I just have to get my Emacs font where it fits on one screen. What the hell here?
So the nice thing with these hash objects, so I basically I create this one object and then I hash it to get my hash. I came up with that when I was thinking about functions that are commutative. And so then I say, okay, well, why don't I just make my arguments to those functions a set?
Oh, no, I override the hash function for the guys who do shit with commutative, like add.
Yeah, because my set, if I make it a set, then it basically seems to work. Although I guess if I had one argument and versus 2 arguments the same, it would collide. So
okay, so I threw in the doc Bertle lookup 3, and then if you want to switch, I'll show you guys some other shit I do.
Yeah, sure.
Let me pull up. You okay here?
Yeah.
Pull up hash things. Back to Emacs. I have to reset my font again. What did I do here? I think I went to 18 or something, and then that scrolls off the bottom of the screen. And they go, yes, that's a little better. Okay, so copy from Bertle. I got a little rot for Java. I got an add hash, does some horrible shit. These are all like 4 or 5 clocks worth of rote after x86, and C2 gets after it. It's really quick. The other thing to show here is I have this repo quality check. which prints out a reprobe histogram, and a hash quality check, which says every 1,000 or 65,000 puts print out the reprobe and the hash quality printout. And that helped me diagnose bugs where I was getting really horrifically bad hashes. And that was necessary as I started doing larger programs. So don't trust your hash function, and a good hash function's worth a serious integer factor speedups. For 4x to 10x for bad hash function to good hash function. It's like big numbers, stupidly. And I have a bunch of support for hash functions, and this is a utility library. It just happens to include all the hash bits.
Yeah, just anecdotally improving our hash functions for our kind of our intern constant pool gave us about a 20% speed up overall.
For compilation.
No, that's runtime and compilation.
Oh, okay. Yeah.
Let's just see. Yeah,
Runtime
commented
only
out right
because-
now
because
in my
we're-
main hash, my main type and turning table is like reprobe quality check. And quality check. Yeah, I got a couple places where I have it turned off. Here's another one that I diagnosed it a while ago and fixed myself up a big number speed up on the try all types against all types on all nodes, quartically deep loop, where I was doing, you know, tens of millions of probes, or before the test was done or something. The test was running for hours, turned into running for minutes when I got my hash table fixed. So it's worth getting a good hash function. And if I do this, we got here for hash code. Hash code says load my op as a small integer for all my defs. If I have a def, grab his user ID. Defs dot, this is an array, and store it in. So it's ugly for the standard nodes because that's good enough. For fancy nodes like constant nodes, who only difference is their opcode is their type, the types have to be wildly different hashes. So that one was constant, and con node picks up a different hash. Takes the hash from the type and not from the inputs, because there are no inputs to a con node. It's a constant, it has no inputs. So
yeah. You don't hash the actual constant value?
that is the hash code for the actual constant.
Oh,
Under
okay.
T is the constant.
Oh, okay. Okay. Oh,
That
right.
goes
That's right.
Type. That goes,
Type is
that
the
goes
constant.
exactly to type.java. It's this thing,
Right.
which is wherever the hash code. Now, hash codes on my constants get like crazy. So there's a starter, but then if I go to things that are recursive, they ask the same question recursively unless they have cycles.
Yeah.
And then they have to get a good answer for the cycle without going recursive, because you can't go recursive on a cycle, it runs forever. So there's some crazy shit for things that go like, here we go. I think tuples don't go recursive. Let me see here. Compute hash is okay. So just a shortcut here. The hashes, because they're complicated, I cache the hash on a node. So once the hash is computed once, you have it. So this guy just runs his inputs, including grabbing one layer deep. Because he's not involved in any recursion, I don't have to call the hash code function. I just call t.hash as an integer. So he grabs a bunch of ints, does the same rotation math you saw earlier for burtle.net, and gives me a really nice hash. But if you look at type struct, which is involved, structs point to fields, point to pointers, point to structs, has a recursion.
Why don't you just hash like the node ID? Why bother? Why recursively hash the containing object?
Oh, I'm sorry. For types, it's different. For nodes, exactly what you just said. The default for nodes is I hash opcode and inputs.
Opcodes and IDs. Yeah, that's what I'm doing too.
Opcodes and ID inputs. Yeah, so this is it. This is the one. This is the hash for nodes.
Yeah.
Code right there for my inputs. If you like to spread it out, you know,
Yeah.
And there's .uid, which is the unique ID.
Yeah.
Top line of my current Emacs says unique ID, dense numbering on nodes.
Yeah.
That's the standard node input now, or hash code. There are variations I mentioned. Types are different. Types, I have equirecursive types. So I have cyclic types, and two cycles that are the same cycle are in fact the same type and turn into the same type after interning, which means they have the same hash, which means while types have a unique ID as well, I can't use them in a cycle or in general as part of the hash, because if I make a hash with a different unique ID, but it has to hash to the prior existing guy who's the identical match to it.
Yeah.
So types do not get to use unique IDs for
Yeah.
their hash function.
So here's so what I was hoping to do, I don't know if this is going to work because I hadn't thought about hashing, but I haven't done much of the type code. I built the lattice gadget. I don't know if I showed that last time. Well, no, we walked through the lattice that I was doing. So I thought, why don't I make my type lattice from in an actual graph, which means that I can't instantiate all the actual constants. So then I created a placeholder for the constant. So like, and then I just said, okay, well, I have to be able to deal with multiple unique constants. So I'll just have an A and B version of each one. So I never have things with more than 2 arguments. And so I've got like a, constant scalar.
So,
which
okay, so
anything. And so then if I want to do a meet or a join on those, I can't just say const because it'll join in ones that aren't the same. But if they're 2 different constants, it doesn't really matter. I just know that I say, if it's the left argument, I say const scalar A. If it's the right argument, I say const scalar B. And then when I meet them, if they're not both the same, it'll like follow the lattice to.
So I do these lattice games. You're talking about, you build a Hesse diagram for your lattice, but you specifically build it as a graph. I've thought long and hard about doing that. I have a rich enough type lattice that I don't think that's the right approach for me. I don't know that that's not going to work just fine for you.
Yeah.
To do the constant things, you're going to want to admit that you have a node in the graph which is representative of a bajillion nodes, one for each signature constant, and just treat that as part of your doing meet. When you do your, common, most, whatever, greatest common ancestor, you're doing your meet and you're joining the lattice, just say, oh, I've parked here, I have an additional test that 2 of these guys are the same or they're not, and if they're not, I have to go on to the next point in the lattice. I can't stop here.
Yeah.
That will cover, and that'll just make it theoretically a general solution.
Right. Yeah.
So stop at 2 and hope they're always different right up until you have a 3rd guy, and then
right. So I should just have some sort of like
extra
little container that has the actual value and the node in the graph.
Right. Like all my types start with the name type. They'll inherit from the basic type object. That's the container you're talking about. But I don't have a graph representation. I have instead of meet function, which given 2 types computes the new one, which leads to all kinds of errors when you get really complicated, because you just make mistakes and reflectivity and symmetry and a bunch of other properties I want out of my type lattice. So I have some very aggressive testing, and then I have, as you found, the test lattices where I describe a lattice like a graph and confirm that in fact it's a lattice, as opposed to it's a pretty graph, but it happens to not be a lattice. There's plenty of those that look like a lattice.
Yeah.
Where's test lattice here? So ugly one, see if I can find a shorter one here. That's the test for the test lattice. I'm gonna find an ignore. Here's test lattice 1. Is there even simpler one here? This structure, see a comment here, this structure is tested to be a lattice. But now I go down to test number 1, where I try to make a ascogram diagram. I describe a lattice as a graph by nodes and edges. And see the add ignore in front, because this is not in fact a lattice. So if I at the bottom and I run the test, this lattice right here, this test line, it prints and says, you're not a lattice because, and fuck, it doesn't look like a lattice. But sure enough, the tester pulls out 2 places where there is no meet or join. And so, you know, it ain't a lattice. Suck it up, buttercup. And that makes, like in my case, nil problematic. And I have a bunch of variations of things. So anyhow, all I'm saying is the graph thing is a cool way to visualize the type of system. And if it's simple enough, you can probably correctly decide you're not a lattice. And if you get complicated and have lots and lots, you probably want to test it, confirm that you're actually a lattice, or your constant propagation algorithms will all be wrong.
Yeah.
Da-da-da-da. What
Yeah.
else? That's a lattice.
I haven't gotten really into using it yet. So all the stuff I'm doing, I'm just sort of ignoring the fact that, you know, I've basically put everything as, I think, top or bottom. I can't remember now.
Yeah.
And
sure.
I'm not
That's
sure.
backwards from the industry standard, because they changed their minds between when I was at grad school and when I left. So I always talk backwards to, if you go to the theoretical papers these days,
Yeah.
the top and bottom they use are inverted from what I use.
Oh, really?
Yeah, it
Okay,
sucks.
that's good
I
to
hate
know.
it. I can't talk to these guys sanely without spending 20 minutes getting top and bottom flipped around.
Yeah.
Fine.
Yeah, that's not surprising.
But I would, in a diagram like I show here, scalar is at the bottom of the diagram. It's the one where I have the least information. So I declare a bottom. I only know that you're something that fits in machine register, but I don't know if you're a number or a pointer or whatever.
Yeah.
And then twiddle scalar or X scalar or anti-scalar is the opposite. You could be choice of any integer or any pointer or 0 in any way. And then I kind of have an ASCII-gram layout where I do a split, and then join. It makes a classic looking essay diagram straight out of the Wikipedia page, and it's not a lattice.
Right.
So that's the bug to watch out for. They can look like it, but ask the question, because you can be wrong and then you get screwed.
Yeah. Okay.
Yeah, let me stop share here. It's just like whatever. Fine.
So anyway, I've been having fun with this.
Yeah, sure. Yeah. It sounds like you're making the right kind of progress.
Yeah, I feel like I'm making pretty steady progress.
Yeah.
You said you converted most of your passes into worklist algorithm work. Do you have an example of a pass that you were not able to convert to this form?
Me?
Yeah. Do you still have to have a pass before or after you do the whole worklist thing?
Well, I'm gonna have some passes. So I haven't figured out what point I'm gonna put select instructions and stuff like that back in. If I do that after I've gone, so the way that I had it previously is I sort of go to basic blocks and then I go through and select instructions. And then after that, I was doing register allocation, some patching and cleanup. And then I would just encode the blocks and then generate the bytecode. But
that's very similar to what C2 does at that point. There's a lot of things that are optimizations, but then I get to a point where I stop and I say, unwind the C into basic blocks, put fee nodes in the basic blocks where you're calling it selects, fine. Now do register allocation. Actually, I do anti-dependencies, and then I do register allocation. And then I guess anti-dependencies come in before I do code layout. So that happens first. There's anti-dependencies, there's code layout, including scheduling for execution units on a hardware, including scheduling for latencies, for frequencies, for a bunch of layout things, but that's all one pass. Then there's register allocation, which is its own giant honking thing. There's a post allocation pass to clean up a bunch of extra copies and fees and try to shuffle things around. there's probably a pass to screw with all my uncommon exits back to the interpreter. And then I didn't do bytecodes, I do x86, and then there's go emit x86 code.
Yeah. Yeah.
And there's a pass for talking to the runtime info, compacting it into the form of the runtime ones, like I have register allocation, or the register allocation, I have garbage collection. What's a pointer? The GC walks a pointer description map that's different from the compilers, so I have to convert the data structures. So yeah, a bunch of post passes that are not related to optimization and not related to type info, but to hardware. Machine code generation.
How do you deal with loop unrolling? Do you do that as a peephole optimization?
Yeah, loop unrolling is the easy one. More or less, it's like a glorified peephole. I have a separate pass for it. I clean up other things first, because as soon as you do anything that does code growth, you want to grow something that's already been shrunk. You don't want to grow a big thing bigger.
Yeah.
So there's a giant cleanup. There's a pass that's more or less, it's a pass officially, not a peephole, where I look for loops, and I'm looking for the proper way to nest loops that they have shared common headers, which I get out of my execution frequencies, and I will break shared headers to force a proper nesting. So you have a irreducible, not irreducible, you have a loop here, a loop header, and he's got a back edge like this. I wrote some code, I said continue, that's a back edge. Then I wrote some more code, and I said continue again, another back edge, and then more code, continue again, another back edge, and so on and so forth. Okay. You'll look at those back edges and you get their execution frequencies. You take this guy and you shatter him into nestings according to execution frequencies. So the innermost loop is your hot loop. So that changes the layout of things, but it's in the sea of nodes, the layout's like all bogus. So there's a go find your back edges, go split shared headers so that they're now nested properly. For everybody who I can find an induction variable, so look for induction variables. That is in fact a pattern match. You can go look for induction variables. I change a loop header to be a counted loop header. So I have regions in C2. Once I'm finding loops, so I know your loop header, I change it to a loop node, which inherits from region, but it only has two inputs. The first is the fall through, the second is the back edge, and that's known. But it's still a region node, but it's also now known as a loop node. And then if I can find an induction variable, I declare you a counted loop node. And then I have the innermost loop is the first place to go look at. And I do a bunch of loop ops now. And there's usually range checks, and maybe you don't deal with this, right? So for me, I have range checks and I have null checks. Null checks are almost always loop invariant, but they're tested first time in the body of the loop. So I want to peel one iteration. So that peeled iteration handles all the tests that are done for the first time in the body in the peeled iteration. And the body gets rid of the tests. And that's all done with peepholes, because the control flow guy says, hey, I'm a test, but I see a prior version of myself in the control flow graph. Some control flow steps removed, there's another version. I test the same way that guy did. And if he followed off for null pointer to on some other place, he never got to me. So I must be, not null, so I'm dead, and he cleans up. So once that all cleans up, I'm done with the innermost loop. It's known inner. It's node counted. If it's going to be counted, it has some range checks. I do a thing that is not in people that I do range check elimination on. And that's the one where I make a post body and a pre body, and I put iterations at the edge cases in the pre or the post where I test the range check the hard way. And then I kill the range checks in the middle of the loop. When I'm finally got an inner loop that I'm not going to do any further range check elimination on, if I declare it small enough, and that's basically done like a peephole, I just count the body because I know it's a back edge only loop. I can start at the top and I can go to the bottom and I can walk backwards, and I can check the data edges don't get only inputs from the other side. There's some shit I do as part of that where I have a list of guys that are in the body conveniently. He's small enough, I say unroll. And in my case, unroll means I clone the entire body, patch the edges through. The fall off test is declared dead, and the fall in only comes from fall out, doesn't have a back edge or whatever, so it's an unroll thing. And that made the trip iterate twice instead of once. And I moved the odd iteration into the post loop typically. So I changed the trip count on the post loop to do a fucking and or mask stupid game to pick up the odd iteration. And then the main body, I let the people clean up the duplicate addition to the induction variable, and the duplicate test gets cleaned up, and that's all done with people's. And then usually there's a lot of shared shit that cleans up. But if you're doing like a Daxby, Saxby, Blaz style loop, you still end up with a, instead of one load and an add and a store, you get two loads, two adds, two stores, and no null checks, no range checks, and you declare that's pretty small. You get an increment for the counter now, +2 and less than max, and that's pretty small. Go again, and then I just reapply the unroller, and he doubles again until the loop gets whatever my limit is, and I say done.
Right. Yeah, I was okay. So have you ever just another idea that I had was if you've got a big loop that maybe loops, I don't know.
So see, big body of the loop or big trip count on the loop?
A big trip count.
Okay, and a small body.
Yeah, small body. Do you ever do like work it like basically unroll the first and the last iteration, but then leave the main body of the loop so that you can kind of deal with the special cases? Maybe
that's what I just said with the null pointers. You unroll the first specifically to get rid of the special cases that happen on the first round through.
Yeah, but do you ever do the last as well?
I don't, but if it has a range check, I'll have a post loop, which usually picks up one iteration and then does the last. And it's because I don't typically see the last has a special case. Like null pointer checks as a loop invariant test that happens the first time loop body, really common.
Unless it's not a normal power of 2. You're going to unroll and be like, I'm going to do these 8 at a time, and then I'm going to do the last 3.
Right. So then if I've done the unrolling, I'll pick up 8 at a time, and then I'll pick up some odd count depending what n was coming in. The trip count was some number. I did, mod 8 and subtract whatever, and then and off the last iteration. So those went into the post loop. But I don't know that the post loop follows. So I don't know that the last count is always special, that it's exactly happening afterwards, and I don't have to do it in the main body, because typically I don't see that. You might have a different situation where somebody says, I have an edge case, and my edge case does something different at the end edge. The beginning edge for me is always usually some guy wrote something and there's obviously a 0 for his starting edge, and he's got a -1. He's got an edge case, and he's testing for, is the induction variable equals 0? Don't do the -1 case, because he's got a stencil calculation that's got a 3x3 grid. He's walking over a big array, and at the edges, you have to chop the head of the tail. For me, those all turn into range checks, which do in fact get peeled and thrown off in the end, and there are no range checks in the middle. And so I know for a fact that the -1 +1 on the stencil will not overflow or underflow. So I don't have any special thing there. That I'm just doing a 3x3 vertical stencil.
Yeah. Okay.
And in fact, after you do some unrolling, I will fold the stencils up, the partial stencils, and what we call scale replacement, put them in the registers, do all the right things with that. But that's all done with peoples. Like after a loop unrolling round, you run the peoples until they stabilize out, and then you look at the loop again.
Yeah, right. But the loop unrolling, it's a separate pass, you said, and so you're going back and forth between these passes, sort of iterating until you
yeah, so not quite. It's a little simpler, more straightforward. There's run the peoples to everyone's stable. There's during running the peoples, I look for things that are loops and counted loops and loop headers and split things. That's all done with peoples. Okay, once I have that stabilized, I guess not quite. I have an incremental dominator tree I'm running during the peoples that lets me find the loops directly. But counted loops and simple loops are all found without any further ado. But complicated ones, you have to do a loop finder, which for me comes out of the incremental dominator tree.
Yeah, I implemented that stuff when I did the first SSA algo.
Yeah, okay, fine. So if you skip the incremental dominator tree, then you need a loop finder pass. Okay, having found loops, I I then go to a big heuristic that says I need a pre-loop typically. I need a post loop if there's range checks that are going to fail on me. I insert the pre, insert the post, and I insert things in the graph to prevent the pre and the post from dying for having no trips during later rounds of p-polls. I run the normal iter, which cleans up the null checks that are done now in the pre-loop, which runs at least one iteration. And then I only do the unroll piece, like the pre and the post bits get made. Then I do the range check thing, which pushes them trip counts on the pre and the post and kills the things in the middle. That's another one, happens one time only step. Once I have that all done and the inner loop's as tight as it's going to get, now the unroller flips with the iterator cleanup back and forth. And
Yeah.
having said that, I call the iterator people iterator all the time, everywhere, because it's constant in the entire size of the final program, constant in the entire size of the original program. It's super fast, it's super cheap.
Right. Yeah.
I don't care if I call it. It's all no biggie.
Yeah. So why do you have to put something special on the pre and post loop blocks to make sure they don't get killed?
Because the trip count on the pre and the post might, for a brief time, be like, say, exactly 1. Like the pre-loop, when I first make it, I say, you're actually not a peel, you're a loop. You have a trip count of 1, which means a little bit of constant math will tell me the back edge is dead and will never happen, which the p-poller will totally clean up. Because people write stupid Java programs that trip exactly once all the time, and I can prove it. So I clean up those, and you're not a loop no more, and then you're just some straight line code, and then you got folded and everything else, and Okay. And then once I've cleaned up and I decided to now do the range check elimination, I'm going to adjust those bounds. So that loop can't have disappeared on me. I got to have it still lying around. So I put a node in the graph called the opaque node that you can't see through, the p-poller isn't allowed to peek through. And I just hook it into the graph right around the range check, so the loop trip count test. So when I come to adjust the loop trip count bounds, the loop's still there. I adjust the bounds, and when I'm all done adjusting bounds, then I yank it in case, in fact, it trips 0 or 1 time, and then the iterator knows it or the p-poller knows it and can clean it up. And that happens for simple loops. Some guy writes for I equals 0 to n, I less than n. You'll get a pre and a post for the range checks, promptly followed by they're all dead, they have no trip count, and in fact, the range check's statically provable as well, and it all disappears out from under you, and you have whatever simplest possible straight line code for the operation. So it all folds up if you have simple cases, but if you have something nasty going on, like my stencil with plus and minus at the edges, you had to test on the trip count for the pre and the post will be non-zero. Something like that.
Okay.
The other consequence of this game is that if people write really trivially dumb micro benchmarks and I can prove there's nothing exciting going on, then when I do my unroll and I put an odd iteration, I put the unrolled odd iteration afterwards, not as an adjustment to the trip count. I think I said before I adjusted the trip count of the post loop. I think I put the entire odd iteration with a 0 test around it. You did or you didn't do the odd iteration. And what that means is that people who say for I equals 1 to a billion, XOR I plus whatever, I'll be able to compute that as a power of 2. So your loop will go down to billions by powers of 2, and you'll get 20 or 30 total iterations, not a billion. And that'll be the micro benchmark will be 10 milliseconds in the interpreter, 10 milliseconds in the JIT, 10 milliseconds to run the 40 iterations instead of the billion, and it's done. And the runtime is independent of the trip count. A million or a billion is the same runtime, because that's how long it took the compiler to tell you. And here's your answer. It's 17 or 42 or whatever it's going to be. Yeah. There's a lot of micro benchmark war history there.
Yeah, it's you always have to be careful when you're doing benchmarks on the JVM.
Yep.
Yeah. All right. Well, I think that's all I can handle for new information in one session.
Yeah.
So.
Yeah. I get it. I get it.
But it's awesome.
Yeah, you're welcome.
Thanks. Yeah. And well, I guess next week I'll have I
Different.
almost have stuff working now, but next week
There
I'll
you go.
definitely.
So on the front of, and I stopped to go do tool improvement. Half of this last week for me on AA was looking at large complicated tests to produce large complicated types. And if I made some minor change to things, the type changed a little bit. And then I had to go produce another golden rule instance of that type. Was hard. So I wanted to parse the type as a string. So I had a parser. And the parser was parsing the strings that I was using in tests. And I had a pretty printer. And nary the twain should meet because I could read the pretty print. But I finally decided I wanted the pretty print to put something that the parser could parse. I wanted it to be a bijection. And lo and behold, I had all kinds of places where I was ambiguous, multiple different parses going on, be possible, unable to parse this, unable to print that. So I spent half the week or 2/3 the week doing a bijection for the pretty print. So I had to change all my prints so they're all a little different, but now they're not ambiguous. And
Yeah.
I can take the output of a execution piece of code and dump that in the golden rule as, and this is what I expect it to be.
That's so worthwhile doing. I always do that too. It's annoying to write, and sometimes you have big chunks of code. Like people might wonder why the hell is this here, but it's amazing for.
And during the debugging process, it has this incredibly annoying behavior that IntelliJ calls the toString that you're middle of changing, you have breakpoints in. And he says, I half printed and then I hit a breakpoint, and on the big yellow boxes, and I did a breakpoint while printing this, covers up the thing that he half printed, and you can't see it till you click away the damn yellow box. Or he, inside the pretty printer as part of the debugger, he called the thing which recursively called the thing, and he goes Stack Overflow while trying to just dump your guts because your dumper is not working yet.
Just right click on that one and choose in the debugger. You right click on it and say, don't call the toString on this one.
Right. And of course the answer was exactly, I wanted as much toString as I could get because I'm looking at what it was supposed to be. And I wanted to single step the thing that I was staring at, but that was coming out of the debugger's toString. So I had to breakpoint before it got there, and then I ran it. It is just a pain in the neck to debug these things. And then, and then once they're done, they're a joy to use because you can just dump one into the other and you're all happy with. And in fact, I have the piece of the commented out line of code now I commented out that says, if I do a toString, take that string and run it through the inverter, the bijection inverter, and assert that I get the same type back. And the other guy has the reverse as well. If I parse a string into a type, pretty print it, make sure I get the same string back.
Yeah.
Fun stuff.
Those are perfect for property-based testing. And you get them all.
Yes. I have a bunch of tests now around the toString being a bijection as well.
Yeah.
Fine. Anything else from anybody? We could go early instead of late. Last 3 months, 4 months for 2 to 2.5 hours, maybe 1.5 hours.
I mean, we solved SSA today. I think that's pretty good.
Okay. Well, we can declare victory for the Alliance and move on. I'll go get lunch and go back to overloads. Ta-da!
Back into the sea of nodes.
And you can go back to Sea of Nodes. All right, let's declare victory for the Alliance. Until we meet again.
All right.
All right.
Bye-bye.
You did say overloads. You didn't give an AA update. Has anything meaningful changed or just more overloading?
More overload testing revealed more weird, funny things. I can pull up exciting looking recursive overloads, and overloads is showing up in bizarre places that turn into, hey, what do you do now? And the Hindley-Milner unification part is stable and working fine. And the flow side of things has to know what Hindley-Milner decided for which way the overload resolved. And I'm now figuring out how to tell, like, Hindley-Milner does resolution between two types. and flow does the type at a node. So I have to take, I did a resolution between two types. Somewhere there's a node involved that says at this node, this overload resolved this way. And the typing system alone, the Henry-Miller typing system alone knows which overload choice got made and where it got made. And now I have to teach that to the flow side, so the flow side can say, oh, and at this point, a decision will get made. When it gets made, I can now pick the two choices. Until it gets made, I can only pick the join of the two choices. So that's where I'm stuck at the moment. It's not stuck, but that's where I'm halfway through. You know, fine, I can pull up, stop one behind, right? Let's see here. What are these? What are some of these evil ones? These are all ones I threw out before. They're not too evil. I got further down the line and made more evil ones. Like here's some hideous ones. I'm trying to think if there's a simpler hideous one that's not out of control. That's an easy one. Oh, here's a hideous one. Okay, so let me throw this into the Google Doc, which I should share. I shouldn't go here because this will take forever today. Let me go find the share button. Share the Google Doc. Yes, share. Let me go clean this up a little bit. Which one did I copy here? Did I get the bad one or not? Yeah, okay, so fine. So here, red is defined to be, oh, stop the capitalization, Google. So I'm in a function, it has a predicate, test the predicate, might as well say random. I'm an overload of a 1, 2, 3 and a string red, or an overload of 4, 5, 6 and a string blue. I want to decrement the red part. I'm making, you know, this function must be called make a lighter color. Decrement the red part and change this to cat. Here, I'll do it this way. This makes it a little more, a little easier to read. So this says subtract, you know, let's do sub red and 1, 1, 1. So I'm going to take your color, it's red or blue, and subtract 1, 1, 1 from it, from the integer value. And there's a string value. I'm just going to append a light. So it's light red or light blue. That's the goal of this piece of code. The funny game here is that I have two overloads that are otherwise unrelated to each other. And they might have different arguments or different layouts or whatever. So my rule is if I merge two overloads that are unrelated to each other, they have to unify at the, they have to resolve at the if. So I have to know that this red is actually 1, 2, 3, or it's the string blue. Or it's a string or it's an int. So this one is like code I can't do. But I could have the make a color. How about I call this make color? Is a function that takes the hex and the string and produces an overload of hex and string. Okay. And now I can say red is make color of, well, I'm going to do this the 1, 2, 3 and, you know, quote red. And blue is the make color of, you know, 4, 5, 6 and blue. Now red and blue are in fact done off of the same overload, just called in two different contexts, but it's the same overload. So I can do an if, you know, predicate red or blue, and then I can call, you know, make light on it here, whatever, make lighter. Of this. So my lighter color is whatever. In this count here, and here make lighter is the subtract game. So make red, make blue. I have a make lighter, which is a function which takes a color and produces a make color, where he does sub from the color 1, 1, 1 and concatenate light onto the color. So the second one I should be able to go do, and I'm currently screwing up on, it's fine. This is what the debugging's about, but it says, because red and blue come from the same overload, there's exactly one overload here. This one overload, and it's not two syntactically different overloads. I can now, in the if, the type for the if statement alone is, in fact, that one overload type with different members to choose between. And make lighter also makes me another overload color.
So if I understand this correctly, these overload types, you can call functions and it'll figure out which of the type you want to use.
Yeah. Effectively, they are saying the typing system will pick the one choice out of all the choices that is correct and doesn't have a type error. And if you have multiple things that have that don't give you type error that correctly unify, then it's an ambiguous overload. That's an error.
Okay, so if you made an overload of like an int and a float and then tried to add to it.
Yeah, I would say I didn't, ambiguous. I can add either way. You're ambiguous now. This one up here is a little differently. My first case has the problem that at the time I unify, I'm unifying two different syntactic overloads, and I don't get any promise that they don't have extra things in them, such as, pretty printer is some function that I put on blue but not on red. Or
Well, what if you had like, you have this color unit, what do you call this type? It's a
is an
unification
overload type.
Overload type. And
Well,
what if you had like a color overload type and then you had another overload type which had like an int and a color?
Yeah, exactly.
So then you could still theoretically do string operations on that, but any int operation would be ambiguous?
Yeah, and that's a choice I can make, whether or not I declare ambiguous up front, or I allow you to say, yeah, there's only one string and it works, but if you do an int, I'm going to blow up on you. And that's where I'm at right now, in fact.
Wouldn't you always have things that are ambiguous, like toString and stuff like that?
Well, toString, okay, so the reason I'm going on here is so I can have ints and floats have operators like add that can choose between int plus int and int plus float and float plus int, float plus float based on overloading. So it's ad hoc polymorphism for overloading, exactly for int and float addition in math. toString itself might be, if I were to declare toString in the language, then toString would just be an overload. And the toString would be, for instance, an overload of a function to whatever, print an int, print a string, print a float, print a function, or whatever it's going to be, right? And then later in life, I would say something like, oh, I can say toString of 1, 2, 3, and he picks out the print int. And I could say, toString of 3.14, and he prints out the, print float. That would be how I'm going to.
But if you did that against a color.
Yeah, my current toString won't know what to do with a color. So it would simply say, I can't resolve this. So it's ambiguous. No unification possible between color and any one of these 4 choices I have here.
But does the very existence of toString invalidate your color object?
No, I just can't call toString on color.
Oh, okay.
But because this toString is limited, it only does 4 types. I could have another toString that understands color, or I could extend it to add a color to it, or I could have it understand overloads in general. I could say I have a print overload version that takes anybody's overload and does some printing thing, however that does.
Right. Huh.
So that the observation I made over the week was I cannot unify this first case here because the overloads are different. And I can, this one. And it can unify here. Because they come from the same syntactic element. And then the action of whether I'm going to force a resolve now or declare that your result is an overload is based on the syntax. So the first example up top here where I say pred and red is this and that, I can't do in how I use it. But there's another version of this guy which I can totally do. This one is okay because I'm going to do this. Here, exactly, red must be an int. So I'm going to pick here, each of these has to be the int version. And it resolves pre the if in both cases. And the if just takes a random predicate choice between two ints.
So
and not two overloads.
the sort of resolution gets hoisted up earlier and done before the assignment to red.
Yeah, usually the sort of rule is I have to resolve you at the first place an overload is used, except where they're the same syntax, and I can stall the overload resolution a little bit further, which is what you want to do what I did here, where I pass colors along and have people have make colors and use colors and do things with them. And then my unification side is working well here, and my flow type is getting confused on where he decides that you're an int or a string. And so there's some work to be done. So that's my AA update.
That's kind of cool.
Yeah, I got here because I was, like I said, I was trying to do operator overloading for int math, so you can write fucking C-like code and have like all these functional languages do some evil hacks so you can write C-like algebraic math and have int float widening work as expected. And then they do some evil hack, and the evil hack just like breaks the prettiness of the functional language. And I'm like, okay, I can do both. So that's where I'm at here. All right, now I'm going to declare victory since we lost half the people as soon as I said I'm done, and I wasn't really done. They ran on another 20 minutes. All right.
All right.
I'm going to end it now unless somebody says something.
Bye.
3, 2, 1.
Next.
For real. Till next time.